I feel like it's safe to say that most of us were devastated when they hit us with that brutal cliffhanger, especially those like me who had no idea it was coming. If you haven't watched the movie yet, you totally should, but don't click away. You don't need to have watched it to understand any of what we'll talk about today, and I think there's still a lot of interesting stuff that you might enjoy. Not more than a couple minutes later, I was already searching up when the next movie was releasing, and that's when it hit me. Beyond the Spiderverse. Beyond? What does it even mean to go beyond an infinite multiverse? Can you even do that? Well, after some thinking I realized that, if the Spiderverse is the infinite set of worlds where Spider-Man does exist, there's still all the infinite worlds that don't have a Spider-Man. In other words, the Spider-Verse is only an infinite subset of the truly infinite multiverse. But here, I was still wondering, how do we actually escape and go beyond the Spider-Verse? It turns out, questions like these, talking about infinite networks and how things behave in them, are, unsurprisingly, not something only I've thought about in my post-movie craze. In fact, along my journey into this rabbit hole, I found that there's a huge amount of interesting stuff to learn from the fields that deal with these types of ideas. So today, I wanted to share a few of these ideas, touching on small portions of probability theory and graph theory, as well as a little bit of physics, all while diving into this fun context of Spider-Man. If we structure it a bit more clearly, the question that we'll build our way up to answering this video essentially boils down to this. If we start at some point in the Spider-Verse, not knowing where the edge of infinity is, what's the chance that we can wander forever outwards in a path of adjacent universes and escape to the true multiverse? At first, this may seem a bit overwhelming, which is pretty common when dealing with these kinds of concepts that just don't pop up in our day-to-day experiences. After all, we just don't have as much to draw from that can help us. I mean, where do we even start with finding a probability out of infinite outcomes? As with many cases involving infinity, it's really helpful to look at a much smaller finite example first. Let's take this line of 4 nodes, or universes in our context, and see what we can find out. On one end is our warm home H, and on the other is a black hole B. If we start at point C here, with equal chance to move to any adjacent nodes at each step, what's the probability that we reach our home before we're consumed by the black hole? It may not actually be immediately obvious what to do, even with this much smaller example. We are, after all, still dealing with a relatively abstract idea, finding a probability out of infinite possibilities of paths that we can take. In these situations where things may seem a bit unfamiliar, a good starting point is always to look at exactly what we do know, and then consider exactly what we want to find out. What we definitely do know is that we have to move left or right from the starting point, with equal chance to go either way. And what we want to find out is the probability of getting home from point C. So let's just start off by giving that a name. We'll call it P of C, for probability at point C. From here, let's just move on and try moving left or right and see what we learn. If we move left, we've already managed to get home. There isn't really any chance of not reaching home if you're already there, so it's pretty intuitive what the probability is at point H. We can say P of H is 1. If we move to the right, however, it isn't as straightforward. We reach a situation pretty similar to our starting point, where we don't really know how to find the probability. So, once again, we'll just give it a name, P of D. Now, again, we can move left or right with equal chance. If we move left, we're back where we started, once again with P of C chance of making it home. If we move to the right though, we end up in our black hole, and that means we definitely aren't going home. To express that as a probability, we'll say P of B is 0. From here, we've actually gotten to a point where we've set ourselves up really well for what we knew to get to what we want to find out. I really encourage you to give a shot at finding P of C yourself, using the information that we've just discovered. Once you see where to start, everything begins to fall into place pretty quickly. Before I get to the answer, here's a hint if you're still really stuck. Try considering how you can express the probabilities in terms of each other. Give it just one more shot. Since we have equal chance of going either way, half the time we will have the odds of going left, and half the time we will have the odds of going right. To write this as a mathematical expression, we'll say P of C is equal to 0.5 times the odds at H, and 0.5 times the odds at D. Using the same logic, we could derive an expression for P of D in terms of its name is 2. And as we mentioned earlier, P of H and P of B are 1 and 0 respectively from intuition. You might notice that P of C is now in terms of P of H, and P of D is in terms of P of B, both of which we know. So let's substitute those values with what we know them to be. After simplifying, what we're left with looks like a pretty simple set of two simultaneous equations. Plugging the second equation into the first leaves us with this, which we can once again simplify until eventually we arrive at this. And there you have it. The probability of making it home from C is 2/3. By taking stock of the situation when things seemed overwhelming, we arrived at the answer without doing anything too unfamiliar at all. But where do we go from here? How do we start making our way back to our original problem from what we've learned? Well, at this point, I unfortunately do have to make a slight disclaimer. In the sections beyond this, there may be points where it is slightly harder to follow along if you don't have any experience at all with circuits or electricity. Although I'll try my best to make it accessible to everyone regardless of prior knowledge, there may be certain concepts that I won't be able to explain from the ground up. There simply isn't enough time to, for example, go over why parallel and series resistors add in the ways they do, as would likely reduce clarity by straying away from the main focus of this video. However, I've listed on the screen right now all the ideas that should be needed, and I'll be giving a basic description of all of them. If whatever explanations I give aren't quite enough to make sense of the concepts, by all means go and explore more resources yourselves. The first idea we'll look at is Ohm's law. Ohm's law relates key properties within a circuit together, saying the voltage of a circuit is equal to its current multiplied by its resistance. It can also be presented in another way that is more suited for taking voltages between specific points x and y. This form is also quite commonly presented in a rearranged form in terms of the current, which is what we'll be using later. Then there's Kirchhoff's current law. Formally, it states that the algebraic sum of currents in a network of conductors meeting at a point is 0. But in other words, all it says is that, for any junction in a circuit, the sum of the currents flowing in will equal the sum of the currents flowing out, which is a pretty intuitive idea. You aren't allowed to make or lose current out of nowhere. Finally, we need to understand how resistors behave when joined with each other. When they're connected in series, the total resistance is simply the sum of their resistances, as seen on the left. However, when connected in parallel, the total resistance is given by the equation on the right, where instead, the reciprocal of the total resistance is the sum of the reciprocals. But why am I talking about electricity all of a sudden? Well, it happens that a circuit can actually be modeled as a graph, and when we do, something really interesting happens. Let's use the tools I just introduced to calculate the voltage at each point, and maybe we'll be able to spot out what that interesting thing is in action. If we look at our two laws here, you might notice that we can actually plug Ohm's law into Kirchhoff's law to get an expression about the voltage of the point that doesn't require us to find any currents. Setting these expressions up for point A and B each leaves us with this. Now, if we recall what this sum actually represents, the condition is that we sum a term for each neighbor that our central node has, which in the case of point A are points S and B. Using this to expand out the sum leaves us with this equation. All the resistors on this graph are of equal resistance, and so R of AS is going to be the exact same as R of AB. And so let's combine these together into a single denominator. Now, finally, you might realize that no matter what, the resistance on the bottom is not going to have an effect on whether the fraction is 0. And so let's cancel it out by multiplying both sides by the resistance. Once we simplify and rearrange, our final equation looks a bit like this. For eagle-eyed viewers, you might have already realized where this is heading, and if so, congratulations. But if not, don't worry, as I'm always certain that you'll see it if we just change how we write this out. Does this look more familiar? If we quickly do this for point B as well, we'll realize that these equations are exactly the same as the ones we set up for our random walk example. Vs and Vg are also 1 and 0, just like pH and Pb before. Is this just a coincidence? It's pretty reasonable to make that claim seeing as we only have a single, really simple example here, but I'll just have to ask you to trust me on this one. If you want to see this idea come to life in a full proof, I'll leave a link in the description. It turns out, circuits behave exactly like random walks when modeled in this way on a graph, and voltage and probability actually become completely interchangeable. The only thing to note is that while in a graph we're more likely to go to a neighbor down a path of greater weight, resistance in circuits work in the opposite manner, where we're less likely to go down the connections with higher resistance. To make it truly parallel between the two, we tend to deal with an idea of conductance instead, where conductance is simply the reciprocal of resistance. Those with some experience with circuits may have realized this duality is actually super useful to us because using the rules that physicists have spent decades coming up with to analyze circuits turns out to be a lot easier than setting up and solving a ridiculous amount of simultaneous equations. This is especially true when we get to random walks on much bigger or even infinite graphs. We essentially now have two separate sets of tools at our disposal to tackle a single type of problem. At this point, we're getting really close to the stage where we have everything we need to go back and challenge our original problem. There's just a couple more key ideas. Up until now, we've been looking at probabilities of reaching one point before another, given a starting point. However, what we'll actually need for our original problem is called the probability of escape. This probability instead represents our chances of making it to another node some distance away without returning to our starting point. In our previous example, this would be like asking what our odds are of making it to G from S without returning to S after leaving. But how might we find this probability? Once again, this is one of the moments where I really encourage everyone watching at home to try and grapple with this idea yourself, before I get into showing just one of many ways we could approach it. Take a moment to once again map out what we know and what we want to find out, and see how we might be able to get from one to the other. A cool trick with probability is that sometimes it's a lot easier to calculate the odds of something not happening, and instead using that to find the odds that it does happen. We often call these complementary probabilities, where the two together make up the total chance. Now, what we're familiar with is how to find the probability of getting back to S before going to G from any node, right? But if we take the complement of that, what do we end up with? The probability of going to G instead before S, which in other words is our probability of escape from A. So, in fact, we can calculate our chances of escaping just by taking the complement of our chances of going home, which if we remember from earlier is 2/3 for this graph. When we realize this, we're quite literally one step away from finding our answer. All we have to do is consider that after starting at S, we'll always take one step away to one of its neighbors, with the likeliness of each being based on the weight or conductance of that connection. From there, if we calculate the odds of escaping, those are our odds overall past that first step. The overall probability of escape must then just be these probabilities combined and weighted by how likely we are to go down that path. This is very similar to how we formulated the equations in our original context, where we had 0.5 times the odds of each direction. In this really simple case, S only has one single neighbor, and we have a 100% chance of going there. So, in fact, the probability of escape from A is also the probability of escape from S, 1/3. Since we're guaranteed to go to A. And just like that, we've calculated our first probability of escape. It turns out that probability of escape can be calculated by I of S over C of S, or the total current going out of the source over the total conductance of its connections. At first glance, this seems a bit weird and disconnected from what we know. But if we take a moment to really play with how we might derive this relationship ourselves, it turns out to be a lot more intuitive than it seems. I'll also leave a link in the description for that. Now, at this point, I hate to say it, but the truth is our question is still a little loose-ended. We don't actually know what the Spider-Verse is like as a multiverse, and it's pretty hard to tell from what we see in the film. So, what I'll do is walk us through an example of what I think would be a pretty cool structure for the Spider-Verse. But what I really hope to do is give you all the tools you need to answer the same question for whatever Spider-Verse you think exists. Now, it's been a while since we actually saw the question that we've been trying to find an answer to, so let's just take a good look at what we're dealing with again. Perhaps this time you'll see it from a new perspective, with all the new ideas that we've gained so far. If the idea of a probability of escape jumps out at you this time, it's because it'll play a big part in our answer. Originally, we talked about P-escape in the context of reaching a point some distance away without returning to our starting point. Now, instead, why don't we just try and find P-escape as we allow this point to approach infinity? In such a situation, let's see what that means in terms of our calculation of P-escape. If we expand out the current using Ohm's law, we'll see that our P-escape becomes inversely dependent on the effective resistance of the whole graph. If our graph's effective resistance is infinite, then our P-escape will be 0, and we will have probability 1 of returning to our starting point if we wander long enough. However, if it works out that our graph's effective resistance is finite, then we have a non-zero value for P-escape, meaning we have a chance of being free. To be able to find the effective resistance of our infinite graph, we need one last key tool. At its core, Rayleigh's law states that if you change the resistance between any 2 points on a graph, the effective resistance can only experience the same direction of change or remain constant. In other words, we cannot decrease the effective resistance between 2 points by increasing the resistance of any of the edges between them, or vice versa. After decreasing one of the resistances between the points, the effective resistance will only ever also decrease or remain constant, and after an increase, the effective resistance will only ever increase or remain constant. There's also a special case of Rayleigh's that states that when 2 points are at the same voltage, changing the resistance between the 2 points has no effect on the effective resistance. Rayleigh's is really important to us because it allows us to take complicated networks and simplify them into something much simpler that we know how to work with. This is because it allows us to do a certain slightly weird trick. When we see points of the same distance on our graph, we can choose to basically fuse them all together, effectively setting the resistance between them to 0. Since this is a decrease in resistances between those points, Rayleigh's principles justify that this would never lead to an increase in the effective resistance. Similarly, we can split nodes apart, set the resistance between them to be infinite, and be sure that this will never lead to a decrease in effective resistance. What this allows us to do is reduce a really complicated problem into something much more bite-sized. If we take these ideas and return to our graph of the Spider-Verse, you might see really quickly how we can finally find the answer we've been looking for. We've been through a lot of new ideas in a really short amount of time, so just as a refresher, here's all the ideas and tools we've covered in our journey to this point. We've been over the probability of returning home, where we used a step-by-step analysis of how things might develop to form simultaneous equations that led us to an answer. We then went over a few key concepts that were crucial to understand before we got to our next big revelation, looking over quick definitions of Ohm's law, Kirchhoff's current law, and adding resistances in series and parallel. What that big revelation happened to be was the fact that circuits are actually just like the random walks we had been exploring, and now we can steal concepts from physics to make our life easier. Then we talked about reversing our thinking about the probability of returning home with a minor extra step, and how that could lead us to a probability of escape. Bringing the probability of escape into the realm of infinite wandering was the next step, and we looked at how the effective resistance of our graph plays into what our probability will be. But to find an effective resistance of an infinite graph, we needed to equip ourselves with one more tool before we could do that, and so we looked at Rayleigh's principles, understanding how we could potentially shift and bend our graphs to make the problem into something much simpler. And finally, we reached the point we're at now, ready to combine everything we know to finally find an answer. So, if we start at the source vertex S, what are the chances that we'll run off to infinity and never return? Feel free to pause the video and just give your best shot at taking everything we know and putting it all together. The first thing to notice is that all these points in each ring are at the same distance. This means we can pretty easily choose to fuse them all together. We also know that this can only decrease the effective resistance, which is an important observation for later. When we do, what we end up with are 8 parallel connections between each point, from the connections leading to the points before we fuse them together into one. Using the relationship between parallel resistors that we can borrow from physics, we can combine all these parallel resistors into a single resistance, which works out to be 1/8, as all the resistors have resistance 1. And since these rings continue out to infinity, we must have an infinite chain of these connections, where each one has resistance 1/8. The effective resistance of resistors in series is given by simply summing the resistances, so the effective resistance of our graph can be expressed by the following sum. Adding infinitely many terms of 1/8 definitely diverges to infinity, and so what we've proven is that the effective resistance of our changed graph must be infinite. This is where that observation becomes really important. Since we know that the resistance of the changed graph can only be less than the original due to Rayleigh's, then the original graph must also have infinite resistance. Looking back to our probability of escape, this means that unfortunately, in a Spiderverse like mine, there is no going beyond the Spiderverse. Wow, so after a pretty long detour, we finally made it back to where we started. If you've made it this far, congratulations, and I hope you enjoyed the journey. When I set out to make this video, I wasn't actually fully sure where it was going, or even where I wanted it to go. But just from my initial spark of curiosity, it's amazing to me the amount of cool things I managed to discover, just by taking some time to actually walk down the paths that opened. And actually, if you were to take away one thing from this video, that's what I would want it to be. Not necessarily any of the laws or theorems that we went over, but the idea that by truly pursuing our peaks of curiosity, we open our eyes to so much more than we would ever expect. So, next time you have one of those random curious thoughts, I encourage you to find some time to wholeheartedly explore it, and see where that might lead you.